China completed a 26-story building in 5 days using a construction material that isn't concrete. The entire structure was finished in less time than it takes most companies to pour a concrete foundation. Within months, companies in Germany, Japan, and South Korea started racing to copy the technology. Patent filings exploded. Major construction companies signed licensing deals. Engineers who spent their entire careers trusting concrete suddenly had to answer a question they never expected. What is this material, and why does it actually outperform everything concrete can do? Concrete has been the foundation of modern construction for over a century. The world produces roughly 4 billion metric tons of cement every year. China alone uses more cement in a single year than the entire United States used during the entire 20th century. Every road, every building, every bridge relies on the same basic formula that hasn't fundamentally changed in generations. But concrete has a problem that nobody can engineer away. The cement industry is responsible for about 8% of all global greenhouse gas emissions. That's more than every airplane in the sky combined. The emissions aren't a side effect of dirty energy or poor practices. They're baked into the chemistry itself. When you heat limestone to over 1,400 degrees Celsius to make cement, carbon dioxide is released as a direct chemical byproduct. Even if every kiln in the world ran on perfectly clean electricity, the emissions would still happen. This is the fundamental problem that nobody solved for decades. Researchers tried replacing part of the cement with industrial waste materials. Others developed alternative binders from different chemical sources. Some explored carbon capture at cement plants to trap emissions before they reached the atmosphere. These efforts helped at the margins, but none of them changed the core economics enough to matter globally. The basic process of mixing concrete, pouring it, and waiting for it to harden stayed almost exactly the same. None of these approaches questioned the fundamental process itself. Then China approached the problem differently. Instead of changing what goes into concrete, researchers asked, what if you change what you do with it the moment it comes out of the mixer? Fresh concrete is a thick, wet slurry packed with water, trapped air bubbles, and loosely arranged particles. Normally, you pour it into a mold and wait. Gravity does some of the work. Vibration tools help a little. Over time, the particles settle, water works its way out, and concrete hardens into whatever shape you gave it. This process hasn't changed in any meaningful way for generations. Engineers understand it completely. They can predict how it will behave under stress, in cold weather, under heavy loads, and after decades of use. The entire profession of civil engineering is built around the assumption that concrete works this way. But the assumption also means accepting concrete's limitations as inevitable. You get a certain strength, you get a certain durability, you get certain vulnerabilities to water, salt, freeze-thaw cycles, and time. Nobody questioned whether these limitations were actually necessary. Research teams at Tongji University, the China Building Materials Academy, and Shanghai Jiao Tong University decided to question that assumption. Instead of letting gravity and time do the work, they applied mechanical pressure to fresh concrete while it was still wet and workable. The pressure was between 5 and 15 megapascals, which is roughly the kind of crushing force you'd find inside a heavy-duty hydraulic press that's used in factories. The pressure wasn't gentle. It forced the mixture to compact as it was being formed, fundamentally changing the material's internal structure at a microscopic level. What happened next changed the entire internal world of the material. The particles were forced together so tightly that excess water and trapped air had nowhere to go but out. The concrete became dramatically denser almost instantly, like the difference between a loosely packed pile of sand and a compressed block of stone. The total porosity, meaning the percentage of volume made up of tiny gaps and voids, dropped by around 65% compared to standard concrete. That number alone doesn't sound dramatic until you understand what it actually means for the material's real-world performance. This matters enormously because those tiny voids are where almost every concrete problem begins. Cracks start at voids. Water gets in through voids. Road salt and seawater travel through voids to reach the steel reinforcement inside, where they cause corrosion that destroys a structure from the inside out. Freeze and thaw damage happens when water trapped in voids expands as it turns to ice. Reduce the voids, and you fix most of concrete's long-term weaknesses in one move. The compressed concrete becomes more resistant to the chemicals and environmental pressures that traditionally weaken structures over decades. But the most important change happened at the microscopic boundary, where cement paste meets each individual piece of stone. In standard concrete, this boundary is actually the weakest part of the whole structure. It's looser and more porous than either the paste or the stone on their own. It's the first place a crack forms when the material is under stress. Under compression casting, this boundary zone tightens dramatically, with significantly fewer voids than conventional concrete. The lab results were striking. Compressive strength increased by over 80% in the highest pressure batches. Resistance to water intrusion, freeze-thaw cycles, and chemical attack all improved substantially. And here's the part that makes engineers sit up straight. The team achieved all of this without adding anything new to the concrete mix. No expensive additives, no exotic materials, no reformulation of the recipe. The same ingredients, handled differently, produced a fundamentally better product. While this concrete breakthrough was developing in research labs, a completely different technology was being perfected in parallel. This one didn't try to improve concrete. Instead, it asked a different question. What if buildings didn't need much concrete at all? B-Core was developed by Broad Group, a Chinese construction company with a history of doing things in the industry that most people assume are impossible. B-Core panels are deceptively simple from the outside. Two thin stainless steel skins held apart by a precise grid of hollow steel tubes arranged in a geometric lattice. The whole structure looks a little like the inside of a waffle iron, but engineered to a tolerance measured in fractions of a millimeter. The design borrows directly from aerospace engineering, the same basic logic that allows an aircraft fuselage to be both incredibly thin and incredibly strong by distributing stress through a structured lattice rather than brute material mass is what makes B-Core panels perform the way they do. Aircraft engineers learned long ago that you don't need massive amounts of material to create strength. You need intelligent geometry and precise engineering. The steel skins handle tension and compression. The pipe lattice handles bending and twisting. Together, they create a panel that weighs 1/10 of a comparable reinforced concrete slab while carrying similar structural loads. Broad Group had already turned heads in the early 2000s when they assembled a 30-story hotel in 15 days using modular steel construction. This wasn't a concept or a proof of concept. It was a real, completed hotel with guests checking in. B-Core took that approach much further by redesigning the fundamental building block itself. The panels are designed to lock together with robotic fasteners, which means a floor of a building can be completed in hours rather than days. Workers don't need to wait for concrete to cure. They don't need specialized concrete expertise. They need fasteners and precision manufacturing, both of which can be controlled with factory automation. The standardization and automation eliminate many of the variables that slow traditional construction. In January 2024, a 26-story building in Chengdu was assembled using B-Core modules in under 5 days. The workers weren't rushing against a deadline. The system is simply designed for speed, the same way flat-pack furniture is designed to go together without special tools or expertise. All the mechanical systems, electrical work and plumbing are installed in the factory. The building arrives on site as modules that bolt together. The speed isn't a marketing claim, it's a direct result of the engineering approach. What makes this more than just a speed advantage is the seismic performance. Buildings in earthquake zones have a fundamental problem that engineers have struggled with for decades. Traditional concrete structures are heavy, and heavy things are hard to move. When the ground shakes, all of that mass creates enormous forces that the building has to absorb. Concrete is strong, but it's brittle. When forces exceed its capacity, it cracks and fails suddenly. Lighter structures built with B-Core panels absorb and redirect those forces differently. Because stainless steel can bend and flex without breaking, it can deform without catastrophic failure. Seismic testing showed the panels handled shock and vibration with a resilience that conventional concrete frames struggled to match. In regions where earthquakes are a real concern, which includes Japan, South Korea, parts of China, and significant portions of the world's most densely populated areas, that is a fundamental safety advantage that changes how engineers approach tall buildings. B-Core and compression cast concrete are solving different problems, but they're pointing in the same direction. One makes the concrete that does get used far better and far greener. The other reduces how much concrete a building needs in the first place. When you put them together, the combined impact on cost, speed, weight, and emissions is far larger than either technology delivers on its own. News in construction science doesn't usually travel fast because the stakes are high. The consequences of getting a structural material wrong are measured in human lives. So when international interest in both technologies started accelerating within months of major breakthroughs and publications, it was a sign that the industry recognized something genuinely different was happening. Patent filings from Germany, Japan, South Korea, and the United Kingdom now cite the compression casting research. These aren't reference citations in academic papers. These are companies and research consortiums putting legal and financial resources behind the technology. LafargeHolcim, one of the largest cement producers on the planet, signed a licensing deal with Beijing Cement Group to adapt compression casting technology for European prefabricated construction. In Germany, a research consortium ran compression cast concrete trials on a real highway project. Companies across Asia and Europe are exploring how to integrate both technologies into their production systems and building methods. What's driving this isn't idealism, it's math. In regions where carbon emissions are taxed or capped under regulatory schemes, a significant reduction in cement use translates directly into lower regulatory costs. Companies save money on carbon compliance. Governments benefit from lower emissions. In any market, cutting the price of the most expensive ingredient in your product while simultaneously making that product stronger is not a trend that companies can ignore. It's a competitive advantage that no serious company can afford to miss. A construction firm that can build faster, cheaper, and with lower emissions gains significant market share in an industry that's increasingly conscious of climate impact and regulatory pressure. The economics are clear and compelling. The real-world trials that preceded all of this corporate activity were critical in building confidence among skeptical engineers. Bridge decks and building projects constructed with compression cast concrete have been monitored and tested with results matching the laboratory predictions. In Shanghai, prefabricated B-core wall panels used in a pilot housing project showed improvements in thermal insulation and required far fewer post-installation repairs than conventional prefabricated panels. The difference wasn't marginal. It was significant enough that the project engineers chose the material based on performance, not environmental marketing. The numbers that researchers attach to the potential scale of adoption are significant. Life cycle models suggest that meaningful adoption of compression casting technology could substantially reduce global carbon dioxide emissions from cement production. To put that in perspective, even partial adoption by major construction economies could deliver emissions reductions equivalent to removing millions of vehicles from the roads. But turning a promising technology into a global standard is a long road, and it's important to be honest about where that road gets difficult. Building codes in most countries are updated on timescales measured in years, sometimes decades. They move slowly by design because the cost of a structural failure isn't just financial. It's measured in human lives. Every country that wants to adopt compression casting at scale needs its own independent testing to verify the results under local conditions, its own regulatory approval process, and its own trained workforce that understands how to operate compression casting equipment consistently and correctly. This takes time. This takes investment. Engineers need to gain confidence through experience. China can share the blueprints, but the rest of the world has to do the work of adapting them locally. Regulators need confidence. Engineers need training. Building officials need to trust the technology. There's also the infrastructure question. Compression casting requires equipment that most concrete plants don't currently have. Retrofitting existing facilities or building new ones from scratch represents significant capital investment. For large construction companies in wealthy countries, that investment may pay off quickly, given the cost and regulatory savings. For smaller contractors and builders in developing economies, the barrier may be much higher. This raises real questions about whether this technology reaches the parts of the world that need affordable, lower carbon construction the most. The technology exists. The proof is there. The competitive advantage is clear. But scaling globally at the speed the climate situation demands is a different challenge entirely. None of these barriers change the underlying reality of what the science shows. They simply define the gap between what is technically possible and what will actually happen at scale in the real world. Closing that gap is a policy challenge, an investment challenge, and a coordination challenge as much as a technical one. It requires alignment across governments, companies, and engineers. What's clear is that for the first time in a very long time, the fundamental process of making and using concrete is actually changing. This shift isn't happening at the margins or in a laboratory. It's happening in real structures that real people are living and working in right now. That represents a genuine change in how the world builds. The question now isn't whether these alternatives can work. Buildings constructed with both compression cast concrete and B-core panels already prove they can. The real question is how quickly the rest of the world can transition to these methods. Will regulatory approval accelerate? Will manufacturing capacity scale fast enough? Will the climate urgency push adoption? Or will economic caution slow it down? Given that concrete is the second most consumed substance on Earth, with only water ahead of it, whatever answers those questions produce will ripple across industries and economies for decades. Engineers who spent their entire careers assuming concrete was the permanent foundation of construction are now asking different questions. And in China, the answer is already being built.